Thank you, Chris Kaczynski, for that amazing description of time dilation. Next, we've got Dat Lee coming up to describe length contraction.
Keep that in me. Well, ladies and gentlemen, good evening, good morning, wherever you may be. We are going to discuss length contraction. So, gentlemen, don't be afraid. This is not apply to you specifically. So, with length contraction, we are going to begin with an experiment. As is in physics, everything that can be proved needs to be proved empirically. So, experiment number 1. Did you catch that? I'm going to do it one more time. So, if you wonder what I'm doing, what the length contraction as postulated by Albert Einstein says that any object moving with a non-zero velocity will experience a length contraction. So does that mean that as I moved, that I got thinner? Because that would be the best weight loss program in the world. Unfortunately, at non-relativistic speeds, it is negligible. So in everyday life, what you experience as things moving through, you won't see a length contraction, but it is there. However, it will be imperceptible to the eye. So, moving on, length contraction, it kind of breaks several different ideas that we think should be constant. Length should be length, it shouldn't change regardless of where you are. Unfortunately, when we're dealing with Einstein's special relativity, things that we think are constant, they change quite a bit. With Einstein's idea of length contractions, he is saying that when we move at relativistic speeds, that length will contract. Now, when we hold that, we are taking two different reference frames, where one would be stationary and another reference frame with an object moving at near the speed of light. What the person at stationary will see is almost a thin line, because when you move at that kind of speed, your length will contract. However, your height will remain the same. Mr. Hendrik Lorentz actually created a formula to kind of tell us what the length that you would perceive might be. The formula is going to be the length that a person that is stationary will see is the length of the object with the square root of 1 minus their velocity squared over the speed of light squared. So the closer that they get to the speed of light, the thinner the object will be that is perceived. So I did have an example for you here. We are testing the speed of a spaceship versus a person on the ground. So at rest, the observed length would be 200. They're not moving, and neither is the person viewing them. And their height would be 40 feet. Now, when you're going 10% the speed of light, what you're going to see is that the observed length will be 199. So you lose 1 feet at 10% the speed of light. However, height will remain the same. When we go 86.5% speed of light, that's going to decrease by half. So the person on the ground will see half the length of the spaceship than it was originally at rest. Again, observed height will remain the same. When you're going faster than that, 99% the speed of light, you're only going to see 28 feet of the spacecraft. And then when you're going 99.99%, the spaceship that was originally 200 feet will be reduced down to 3 feet. They say when you go to 100% the speed of light, you're not going to see anything. The length decreases so much where it's negligible in the observed length. However, it is still there. So this isn't errors due to observation or errors due to mathematics. This is just what happens when you have two different reference frames and when one is moving at relativistic speeds. So it does change the game a bit. How long was that? 4:44. Oh, cool.
Sweet, man. One take?